Let's now consider the challenge of finding the center of mass of not an equilateral triangle, an isosceles triangle. Two sides here the same, the length a bit narrower at the bottom. And from some things we can get one of the centers of mass, the x direction one, pretty easily just by symmetry. If I cut down the middle, it's pretty clear that the mass on both sides is equally distributed. So if we talk about the x bar, it will be equal to the center horizontally, and depending on how we define our axes here, if we define that as x equals 0, then that would be x equals 0 in this frame of reference here. The more challenging part would be to say, if we wanted to balance this, so turn it over on its side and balance it somewhere else along this edge, where would we have to do that? What's the center of mass in the y direction? Well, that's going to be a bit more interesting, but the same principles we used before are going to help us here. So if we talk about y bar, or the center of mass in the y direction, let's define our y values here as, say, the standard one, y equals 0 down here, y equals 5 up here. Then what y coordinate would be the balancing point in this direction? Well, we're going to have the same basic idea, remembering that we're going to have the sum of the y coordinates of masses times the masses, and then we're going to add up and find the total mass as well, except now we're going to have to look at these masses and find out what they are. Now the challenge here is that the density is constant. I don't know what the density is, but it's going to be, doesn't say anything that about the sheet metal being different at the top or the bottom. But there's going to be more metal down here, obviously at this end, than there is at the top. So somehow we expect the center of mass to be towards the bottom because there's more stuff there if density is all the same. So what does that leave us with? It leaves us with the question of how do we find masses on a small scale that we can then add up to get the total mass of this. Well, I think if we're going in the y direction, it makes sense to start slicing this at different y heights. And what we can talk about is constant y values. So on one slice, the y is roughly constant, and we can find the mass of that slice fairly easily. And then we're going to add those up with an integral and get the value of this moment on top, and then evaluate the total mass as well and see what we get there. Okay, so we have to do slices. We want slices this way because we're not so worried about the mass of each slice, but we are worried about having the same y value, the same distance from the bottom of this triangle to get that factor in our moment calculation or center of mass calculation done right. Okay, let's take a look at how we can find that mass of a slice then. I hope you can see the similar triangles jumping out at us here. What do we have in terms of lengths? We have a triangle down here with 3 by 5, and if we cut off here at y, we're going to have 5 minus y left. So a smaller triangle would have 5 minus y as the height, and it would have some width that we actually want desperately for the base of it. And so we can use similar triangles here to find that the width to 5 minus y is the same as 3 to 5, or the width of our slice is equal to 3/5 5 minus y. Why is that helpful? We need to find the mass of a slice. Let's see how that plays out. To find the mass of the slice, we're going to need the area of the slice. This is part of the area. The other part of the area will, of course, be our usual delta something. We're going to take super thin slices, so the width will be delta y. Okay, so let's talk over here about the mass of the slices. Well, that's going to be in kilograms. Notice we weren't given a density, so we hope it will factor itself out. Let's see how that works. Let's assume there is a density, though. We'll call it delta, as in previous examples, and that'll be in kilograms per square meter. This is sheet metal, so how much does 1 square meter weigh? Then we're going to have the width, which is 3/5 5 minus y. That's 1 unit in meters. And then we also have the other side, the delta y, which will also be in meters. Wipe all that out, and we get kilograms. So let me write that delta a little more clearly. Okay, so if we have the mass of a slice, we can plug that in for both m sub i's here when we go to do the integral. Let's actually do it stage by stage. Let's find the integral or the total mass only first. The total mass would be the integral of our mass of each slices. We're going to add up the slices. So we'll have delta times 3/5 times 5 minus y, and the delta y becomes a delta y becomes a dy. And we're going to slice from, we said this triangle started down here at y equals 0, slice, 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 up until the top, which is y equals 5. Okay. If we do that, we have a bunch of constants we can bring out. We have the delta, we have 3/5, and then we have the integral of 5 minus y from 0 to 5 dy. That can equal 3 deltas over 5 times 5y minus y squared over 2 when we do the integration, 5 and 0. And if we evaluate all that, we're going to get 3/5 delta times 25 halves. Okay, we'll leave it like that for the moment because we're actually going to get some nice cancellations. You could certainly bring that in if you liked. The other half of our calculation is the upper part, which we're going to call the moment. I honestly don't know the historical source of that word moment. It always struck me as one of the more cryptic words that people use in physics, but there it is. It gets used in physics, it gets used in statistics as well. There you go. What can I tell you? The moment is exactly the same integral because we're slicing up the same object, except we're going to have a y out front. So it's it's y times the masses, and the mass is this entire expression here, so y times delta times 3/5, 5 minus y dy. This is our mass here, and all we've multiplied by in front is the y. We can do the same kind of calculation. We get our 3/5 delta out front. That's going to be handy later on to cancel. And then we have the integral from 0 to 5 of 5y. We're going to bring this y inside. 5y minus y squared. Carry the 3/5 deltas, and then we're going to have 5y squared over 2 minus y cubed over 3. All of that evaluated at 5 and 0. 3/5 delta, that'll be 125 over 2 minus 125 over 3. That'll be better known, a half minus a third will be 1/6, 125 over 6. Okay, so we're going to use that piece of information and this piece of information because our center of mass is the ratio, the moment divided by the total mass. So we'll do this on a fresh page. Y bar is equal to the integral from 0 to 5 of y times mass sub I. We'll leave it at that. That gives you the idea. Over mass sub I. And those individual things we found were the mass was 3/5 delta times 25 over 2. And then the other one was 3/5 delta times 125 over 6. And there we see, it doesn't matter what the density of this particular shape was. The center of mass would be independent of that. Just to talk about that for a second, if we talk and see this shape here, the center, the balancing point of it, shouldn't depend on whether it's made out of metal, heavy metal, light metal, wood, whatever. The center of mass should be independent of that, and we're seeing that mathematically by the density canceling out and not being part of the center of mass calculations in the end. 3/5 also cancel, and we end up with 125 over 25, which is better known as 5, and over 6 and times 2, so we end up with 5/3. Okay, what does that mean in terms of our picture? Well, remember the total height here was 5, and we set this y was 0 at the bottom. So if I wanted to know where the center of mass was, it would be in the center and 5/3 of a meter up. So 1/3 of the way up to the peak, that'd be 3/3 all the way up. So 1/3 of the way up from the bottom towards the heavy end, towards the wider end of this particular triangle. And so that makes perfectly reasonable sense that the center of mass would be located 5/3 meters from the bottom of this triangle.